where will you find resilience? REdeploy.
Hello, everyone. Thanks for the introduction. I just want to let you know that I'm very excited to be speaking here, and I've learned so much for the first yesterday and this morning, and it's funny because I did some changes to my slides last night, not like a drastic change, but kind of some changes there. So this talk is very different than I think what I've heard at least from yesterday and today, and this is very a practical approach. So you'll see that it's going to be a lot of things like, well, yeah, don't do that, or hey, this is kind of some older pieces. But really, my thought in this talk was to kind of walk you through a resiliency journey with my company, Elasticsearch. Not my company, but a company I work for, Elasticsearch. So you can kind of see from a distributed system perspective how our developers worked with the product and understanding how it breaks and how it's broken for other customers and users, and what are the things that we've done inside the application specifically. And again, if none of this really applies to you, that's fine, because there's going to be zombie pictures, which is pretty cool. And maybe there's something that you can, the challenge here, I guess, is there something that you can maybe take away from a specific thing that you can do within your distributed system or your process and so forth that maybe can be applied here. So if not, like I said, zombie pictures, so that's not bad. So again, my name is George Kobar. I am not George Potter, so I've been using my brain to think about all these different things. But I'm a community advocate, and again, one of the things that I like talking about is how people are using our software and how to, telling the stories of our developers. And that's kind of the role I'm playing today. And one thing that I wanted to talk to you about, so we have a common framework, is what Elasticsearch is, or the company Elastic, and a little bit about the architecture. So we have a common framework that we can our common language we can speak to. But Elasticsearch is a distributed search and analytics engine. And actually, just for a show of hands, who knows about Elastic or Elasticsearch? Okay, so I think there's a few people that don't, so that's really good. But the majority, I think everyone raised their hands. So it's a distributed search engine that sits on top of Lucene, and which Lucene is an information retrieval library that's written in Java. And after 20 years, it's still being actively developed today, which is pretty impressive. And if you were to take an Uber ride, from the airport, Elasticsearch provides that data to Uber. And it's a complex set of data that sits on top of maps, different products such as UberX and so forth, that gathers all that data to provide where riders are at and where the consumer is at. And if you're looking at maybe dinner tonight, Yelp also uses Elasticsearch behind to provide that data that provides you with does the business open at this particular time based off of Lex 5 miles, based off of Chinese food, based off of a lot of these different parameters. And of course tonight, if you're looking for love, Elasticsearch also powers the algorithm that kind of brings people together. So looking for love in all the right or wrong places. So that's just kind of an example of how Elasticsearch in these particular circumstances is being used. And just really from a high level, it's full text search, metrics, application performance monitoring, log analytics, business analytics, anything that you can think of for search. That's typically what we're involved in. So I want to talk about that common language that I want to have about how our distributed system is built, and then go through some of the challenges or the issues that we've seen, and how the development team and engineering team came by and resolved or helped improve upon resiliency. So we have a concept of, Elasticsearch has a concept of nodes. And these nodes are actually the physical location of where it stores data, and which is where the Java process is located. So this could be a physical machine, a virtual machine, or a container, or in the cloud, right? Someone else's computer. And with multiple Elasticsearch nodes, they create a cluster. After using a quorum algorithm, and we'll talk about this a little bit more. So the logical collection of data, this could be text or numerical data, stored into JSON documents, that's called an index. And the data inside Elasticsearch is distributed across the Elasticsearch nodes in a partitioning method known as shards. So as the data is being written into the physical location, you can see that the data is not evenly spread out, but it's just written to particular nodes that are all kind of partitioned out. So we also have the concept of replica shards. Right, so let me back up. So we have primary shards, that's where the data resides. We also have a concept of replication that's distributed across the cluster. This is called replica shards. And you can see here that the green is showing as the primary, like P0, P1, P2, but they also are replicated across to other nodes, just for data resiliency. So one of the advantages here is not only do you have a copy of the data, but on read, Elasticsearch can choose either the primary or the replica shards. So the advantage of having the primary to be read off of, and also have replica, it also serves as another point where you can search the data on. So if a node happens to drop out of the cluster, or from a network outage or a failure, the data is still available on this replica shard. So Elasticsearch also can promote a shard to become now a primary, and then begins to replicate that data. Then begins to replicate that data over onto another node. Any second now. There we go. So anyway, yay! So now that this is keeping in the rules of making sure that the replica shard, or that there's data resiliency across the distributed system. So data replication happens at the per shard level, and it's independent and highly concurrent. So as an example, we have a primary 0 and a replica 0, and so on. We have a primary 1, replica 1, and so forth. So writes will always go to the primary first, and then followed by the data replicated to the shard. So as data is written down to P0, then it's replicated to R0, and so forth. So almost done with the architecture. Hang with me. So at the cluster level, we have a cluster coordination metadata replication layer. That's a handful. So the metadata determines which of the indices are part of the cluster. Also the schema, which is very similar to the mapping or within a relation database. But the metadata also shows which nodes are holding the primary and the replica shards, and it's also where when the shards are in sync or out of sync. So all of this data is captured into an object that we like to call a cluster state. And this object is shared and available across all the nodes within the cluster. So this is very important to each node that is aware of where the data resides and the coordinating of new search requests that come in. Okay, is everyone still alive? Okay. So very beginning in our Elasticsearch journey, back in 1.0, and this is approximately about 2014, very few clusters, clusters had very few nodes. So when we looked at issues or recovering from failures, it was relatively easy. I'm kind of using my air quotes here. However, if we had a node that had a power failure, one of the big things that we had to think about was, because this was we're writing data into Elasticsearch, and all this needs to fill up into a memory buffer, and then of course commit it to disk. But how do we capture that data if it's missing, or if it powers off and it's before it's committed to disk? Well, one of the things that we started to look at early is how do we kind of build that resiliency into that particular situation. So one of the answers that we had was what's called a transaction log. So each shard has a transaction log, and it's known as a translog. It's very complicated. But anytime anything has been updated or deleted or written to, it's automatically written into what's called this transaction log right here. In the event of a crash, those transactions, even before it's committed to disk, is written right over to the replica shard. And so this data, let me go back here. So this data, obviously, we're catching as much data as we can before it's actually committed to disk. And we commit to disk, it's typically a pretty costly operation, so we want to make sure we capture all that data before it is. And then one of the reasons why it's a costly operation is sometimes we want to fill up the memory buffer before we actually commit to disk, and then we can kind of proceed forward. One analogy to think about is is if you have a sinking boat and if you have one of those small little cups, it's a lot easier to have a larger bucket to dump all that water out of your boat than a small little cup to dump out. So that's why we allow the data to be written onto a buffer, and that's why we have this transaction log so we can capture that. So part of the Elasticsearch journey resiliency rules is having a translog or write-ahead log. So if you can think about some of these systems that you need to capture data into a long memory buffer, it might be something that you might consider to have or write into a write-ahead log or a transaction log. And the log for Elasticsearch is very simple. It's just a sequence ID and the action that's actually taken. And if this didn't really help out, here's a zombie picture. So when with technologies such as virtualization, containerization, or running multiple processes on a physical host, it's very easy that an entire application could reside on one physical host. For example, here we can see, on this Docker host on your left side, you can have an entire application that happens to reside on there, right? Whether it be, if your Docker host catches on fire, or if you have lightning storm to your hypervisor ESXi host, or if you have Pennywise come and visit you, Pennywise come visit your AWS farm, or if you have a natural event. This obviously can wipe out the entire application. In Elasticsearch, we saw this very frequently when they started using containers to deploy the application. They haven't resided on a lot of different physical container hosts, but not realizing that even with the shard copy and the rebalancing, that all of these nodes can happen to reside on one particular host. So obviously, Elasticsearch is not the only application that's susceptible to this. So even with shard replication to another node, it didn't guarantee that the nodes reside on physical hosts or nodes. So one important thing that we advise a lot of our users on the open source community side is to ensure that you have some type of rules in place where you can start partitioning the data out, or tell the nodes, hey, you cannot reside on the same host. So this gives us guidance, technologies in the software to have rules such as anti-affinity rules, or to specify when the nodes can or cannot be on the same physical host. So in this particular example, on the host that happens to go down, we have still replica data, we have that data on different nodes that also share the common data across different hosts. So if we lose one, then we still have the copies of everything else. So there's a lot of ways that you can ensure that your distributed systems have on separate resources. And one of those things we have is known as, for example, availability zones. So I know that Amazon or even Google Cloud or any of the cloud providers are very keen about this, to making sure that you deploy across multiple zones or multiple failure points, right? Or having anti-affinity rules, specifying what node can't be with this node, or making sure maybe that these two services can be joined together and they go very well together, so they should be on the same host. And of course, there's a lot of other platforms on here that you can use container automation, such as Kubernetes, to ensure that this is possible as well. And by the way, every day, all day on Twitter, it's all about Kubernetes. Even Michael Bolton's singing about Kubernetes. I just had to throw that in there. So for resiliency rules is use any anti-affinity rules or pods to nodes or different zones to be able to distribute your application across multiple failure points, which is kind of a duh, but you still have to at least illustrate these things to some people that maybe not have the experience. And of course, if that didn't help, or excuse me, if that wasn't really helpful here, there's another zombie picture. So something that was also discovered quite early within using Elasticsearch, or within the resiliency journey, is that humans can do stupid things. And I've revised the slide because I've been kind of convinced that not all humans are stupid. Or the fault isn't the human, right? We'll get to that in a little bit. But without administrative guardrails in place, a particular user that may be uneducated can send an unoptimized query which could search across data spanning through the beginning of time. And maybe using a query in such a way that can cause issues to the Elasticsearch cluster. Specifically, maybe that can use all the JVM or all the CPU and would bring down the system. So Elasticsearch obviously, well, it's not obviously, but Elasticsearch is written in Java, and of course, if anyone has dealt with Java, you know this terrible out-of-space memory error. So hopefully no one has any night tremors from seeing this. So one of the things that our developers decided to put into, we needed a way to protect the nodes from health or unoptimized queries. So the development team decided to add a concept of circuit breakers. So these circuit breakers, if a query would result in a high memory issues, it would exhaust the JVM, the task actually would be stopped and it would be logged as a circuit breaker exception. So not only do we have the task of, hey, we're not going to allow this query to run, but we're going to actually stop this before it explodes this particular node. And in that, we can also log that, so then we can actually go back and relearn, okay, what about this particular query is causing such issue? Is there something else that we can help, we can provide those guardrails for some of those users that are using the system? So circuit breakers or rate limiting across microservices as well is also available. So an example, I haven't personally used this, but I know some folks that have, but Resilience for J or Sentinel is great to help with those circuit breaker or microservice architectures to make sure there's some type of rate limiting or circuit breaking across those systems. So resilient rule number 3, man, hold on, I'm gonna put this down here. So the number 3 is, using circuit breakers or some type of rate limiting to know that your system, at to a point that you want to make sure that you take the corrective action or something that you can temporarily pause or stop and report on that is extremely helpful. At least it was very helpful on the Elasticsearch journey, the resiliency journey, not to have a single user bring down a whole set of clusters. And here's another zombie pick. So if we kind of go into today, or we jump to today for the resiliency journey Elastic, we're using, the use cases right now are for petabytes worth of data, and the use cases are far more demanding. So the amount of Elasticsearch nodes per cluster grew, and so did the resiliency and the consistency challenges. So the Elasticsearch clusters became so big, it was necessary for us to start dividing roles up on what the nodes were responsible for doing. So the roles that were kind of devised, for this particular talk, we'll focus on is what's called the master node and what's the data node. And it's to handle 2 types of data within Elasticsearch. So the 2 types of data have very different characteristics. So the data nodes, that's the data that you actually search on, so that's the text and numerical data that's stored on the node itself. It requires a high throughput, it requires a lot of writes and reads, it's very disk heavy. And that data obviously changes. Let's say if it's a time series data or logging metrics data, that data is going to be constantly changing. And as more events that you log, of course, that's going to be very heavy on the system. So and also you want to make sure you have redundant copies to make sure that you have the copy of the data if something happens to the system. But the metadata, on the other hand, that was that purple box that we were talking about earlier in the architecture, does not change as frequent, right? So the metadata is typically small, and the metadata needs to be known to all nodes, so it can, for example, route traffic to the right shards when it's doing searching. Because these 2 different behavior patterns for these data, between the data and the metadata, we had to use a system to manage these data types. The metadata is organized using a quorum-based consensus. And this consensus algorithm is run particularly on the master nodes. So the data is stored using a primary backup replication algorithm, which is run on the data nodes. And these algorithms are dependent on each other. The data replication layer is fully dependent, and it comes to indexing and searching, but it relies on the metadata system to make decisions about things, adding fields, and deciding which data can be called primary. So having all the nodes agree on a common view of this metadata is important to provide a perfect view of the cluster from the outside, or from the client's perspective. So the client can connect to the cluster, but it's also crucial to ensure that the consistency of the metadata is within the cluster. So we have our client here, and we said to ask our cluster, how many ducks are, what's the word duck within our documents? Can you provide how many instances that appears within our system? And so, let's see here. So to make matters worse, ensuring consistency of the metadata is not only important to the metadata itself, but also has a direct impact on the data layer. So the metadata layer determines which shards are allocated to which nodes, and which shards are primaries, and which ones are replicas. So there's inconsistencies in the metadata layer, which leads to two shards believing that the primary at the same time can have the two shard copies becoming inconsistent between each other. The data that happen to be are supposed to store the same data. So if we ask this of our cluster here, and it says, our master node says, hey, this data is actually existing over here, that happens to be a good consistent data, then we get the answer of 5. But of course, imagine that one node has an inconsistent data versus another, but the data ensures that it's the same. This would mean the search node would result in a different result. So we have the same example, but we're going to an inconsistent data, or let's believe the metadata says it's the same, but the actual data on the node is different. We're going to receive an answer of 4. So it's very important that the metadata and the data layer that coordinated well with each other or can cause to data loss. So another common problem is one of the master nodes, and this is again one of the nodes that manages that metadata, would drop off the cluster, or half the nodes become network isolated. So Pennywise visited the data center and decided to take the node down. I don't know why it's Pennywise, but whatever. Obviously, this division here between the network isolated, it's isolated from each other, but it's also still available outside of the system. So this would result in 2 distinct clusters, and thus 2 separate cluster states. So we have, effectively, this was one cluster, but now we have a cluster A and a cluster B. So this would result in 2 distinct clusters and two different cluster states. And this would be result of what we probably know as a split brain. So the metadata layer at this point would be inconsistent, ultimately leading to the loss of data. So many of these issues were known under the name split brain. When more one node cluster is acting as an active master and independently from each other, making changes to the cluster state, and hence the metadata, which resulted in inconsistencies. So one of the most pressing issues here is that, therefore, to fix the metadata layer, we had to prevent these split brain situations. And a lot of these situations came from that the data was not in fact wrong, but it was the metadata that was controlling that. So when we have data loss, it's not even actually the documents that are stored on the nodes, it was the metadata that was actually controlling this piece. So, without too much technical details, which is fun, but Elasticsearch first approached this issue with having humans configuring the amount of master nodes that was needed for a minimum clusters to start. So the notion of a quorum, which was used in a distributed system as the minimum set of votes that a change has to attain in order to take effect. So in Elasticsearch, the minimum master nodes setting determines the quorum size, and it has to be correctly configured for the cluster administrator in order to avoid split brain situations. So in this particular example, that what we call Zen, that's the piece that controls the behavior of deciding which cluster state, or how many master nodes can now come up to the system and the cluster now becomes alive. In this particular example, we have 3 master nodes, and it's a basic majority vote, right? So it's taking the amount of master nodes divided by 2 plus 1, which I think a lot of different applications, whether they distributed or not, use that same type of quorum model. So just another quick example, we have 4 master nodes divided by 2 plus 1 gives us 3. So without going to, however, inexperienced administrators would still incorrectly configure these settings that we put into Elasticsearch. So it resulted in split braining clusters, which led to data inconsistencies. And me, prior to being to this community advocate role, I was on the support team for about 2 years with Elasticsearch. And how many times that I would have these calls with customers saying, hey, I have these 2 weird clusters now, it used to be 1, and one of the first things you investigated is this Discovery Zen Master. What was this configured to? In one particular case, it would be 1 or the default of 3. So here's another resiliency rule that I recently changed because of this talk. Before it was, don't trust humans, but now I just kind of changed that into poka-yoke humans. So who here has heard of the term of poka-yoke? Oh, great. So this is the Japanese term for error-proofing the human, or error-proofing the situation. So last night during the dinner, I think it was Damon I was talking with about this concept of poka-yoke, where they try to eliminate as many errors or causing issues that someone can have within their job. And what we see with Elasticsearch in particular, because we kept repeating or hitting the same issue of split brain, we want to make sure that it was going to be as error-proof as possible so you don't have these particular situations. And here is a zombie clip. So how do you fix, or how do you poka-yoke a human in this quorum type of situation? And I think this part of the talk fits nicely in with some of the other talks previous today and earlier, because I think a lot of people are talking about the modeling and formulas and how do we represent these highly distributed, high complex systems. So I definitely want to touch on that today. So increasingly large clusters and a possibility of a million different node states, we have a way to resolve split brain or misconfiguration, and which we call Zen 2. So I think about this slide, it probably could be replaced with Casey's slide earlier with the network system that you have a million different states across, let's say thousands of nodes as part of your distributed cluster or distributed system. So consensus is getting a set of nodes in a distributed system to agree on something. And that's very difficult, and it's very surprising. Systems like Elasticsearch are asynchronous. So if you can get a distributed system to agree on one thing that's very difficult, then you can then have it agree on multiple things. And that was the first part, is to have it to agree on one thing. And asynchronous, there's no guarantee on how long the operations might take. So if you look at some of these, this example here between the two nodes, we have the messages in between the cluster states. It could take milliseconds, it could take minutes, it could take hours. They could arrive at different times, they could be completely dropped. They also might arrive in different orders that they were originally sent. So despite all of this, we all want it not to go wrong. And what I mean by that is we need to have or design a system which you would have a consensus or for the cluster to still proceed forward regardless if you have two nodes or one node that happens to drop out. So writing the problem down is the first step to understanding this. And writing is nature's way of letting you know how sloppy your thinking is. So if you think about this, if you think about designing a system, even from scratch, or even, hey, we have this complex problem right now, and how do we solve this? And a lot of people, I think, go to writing, go into an architecture map, or trying to figure out this system's connected to this system and how we do that. The problem with writing this down is that pictures are imprecise, and there's a lot of ambiguity that can hide flaws within your system. So what's the solution? Mathematics. So mathematics is a nature's way of letting you know how sloppy your writing is. That was by Leslie Lamport. So mathematics, and I'm not talking about algebra or calculus, but it's the language that was developed over 1,000 years by people trying to describe things very precisely. And if you think about, I think back to my college days or even in high school, talking about physics, one of the great things about physics or even mathematics is it can really describe the problems around us. One of my stories of one of my greatest moments of my physics teacher is like, okay, what problem do we want to solve today? And one of the kids raised his hand and said, how many mosquitoes would it take to stop a freight train? And we spent the rest of the day talking about what things that we needed to do mathematically to figure out how many mosquitoes would it take to actually stop a freight train. And it's an astronomical number if you're really interested. But the math software is instructions. So math can describe instructions. So in principle, we can use math to describe a piece of software. So in practice, there's a problem scale. And the size of the systems that we build means that it could be handled, or can't be handled by traditional tools. So how does one go mathematically expressing a distributed quorum problem? Not all mathematics can deal in branching or corner cases, and in principle, can write a formula that describes this. But in practice, just having a formula to even work with on a distributed system would be way too big. I contemplated writing an equation that was cover the screen, but I think this is sufficient enough. So this kind of enters in the formal methods or build tools to help us deal with models this big. Models that can handle millions of states in a way that we can use and comprehend it as humans. So who has heard of TLA Plus or TILA Plus? Hey, awesome. And it's very good that some people don't know this, so I'm happy to talk about this. So TILA Plus was created by Leslie Lamport, and it's a formal specification language that lets you describe the behavior of a system. So with the support tools, TILA Plus has helped specifically Elastic create models and properties of our distributed system to help discover bugs within the software, specifically around areas of resiliency, and improving upon what we're trying to solve, which was that Zen 2, or Yoka the human. So for, yeah, I like that one. Hey, and if that doesn't really help, there's these two guys, right? Shaun of the Dead. So first we needed to define a set of properties for our formal model. So the first property is safety. And safety property says nothing bad happens. The distributed system never enters a bad state. For this consensus problem, it's all about agreement, right? So you have two nodes that agree upon a state and never have a disagreement. And this problem with the safety property is that you can satisfy them if nothing happens. So that really doesn't do us much good. So we solve this with the other property that also says that something good will eventually happen. And this is just liveliness. And consensus really boils down to a quorum or a majority vote, which we kind of already talked about. You need 3 nodes to determine which node state is up or down, right? So node 1, I lost communication with node 2. Is it node 2 or is it me? Node 3, I lost communication with node 2. Is it node 2 or is it me? Node 1 says, I can communicate with node 3, it's node 2. He's the asshole, or she is, or whatever. The beauty of this is that it's robust and it doesn't need the rest of the nodes for this to work, and the system still moves forward. And this is what I just refer to as double tap, right? Just making sure that you have those two systems, the principal 3 system of having 2 nodes be able to talk to each other and a third that's kind of sitting outside of that. So there are many different algorithms of consensus, but the problem is how to implement them, which involves customization. Anytime that we deal with an algorithm, anytime we deal with a quorum algorithm, we have to integrate that into our code. And this is where the risk for bugs come in, that we can get this wrong. So these potential risks or bugs can persist even if we do testing or code review. So this is why the formal models helps us resolve issues in Zen, or the split-brain consensus issues, to take the human out of the decision-making process for the cluster state. So the 2 models that Elasticsearch used was model checking, which is a tool used for model checker behavior, and it explores all the states the system goes through and verify that all states are good. One second here. And the other one's the interactive theorem providing. So this is just the arbitrary state and more specialized into the tools that we needed to figure out that's going to verify on our model checking. So in order for us to verify the properties of an algorithm, we need to give a formal definition of a precise mathematical definition of your quorum algorithm, or Elasticsearch quorum algorithm. So TILA Plus allows you to use formal specification languages to provide such definitions. So TILA Plus are written in a formal language that combines the temporal logic with the set theory. So specifying an algorithm or systems in TILA Plus is usually done by specifying the initial state, then the next state. So it's essentially a state machine. So in TILA Plus, the state is described as assigning values to the variables. So 1 variables and the number of variables for that no logical state. So there are very different possibilities of model systems. So you're not concerning yourself with the details here. So the most important part of this is then to define how the system transitions from one to the next. So here we have to think about the atomic steps that are that's used in the algorithm should look like. As what the model should be a distributed system, nodes should be able to change the state independent of each other. So if the request arrives on one node, then the processing of that request should be independent. So now that we have to deal with the concurrency, let's look at how the individual atomic steps look like. It says that the node, comes in as a publish request, that it's going to determine the first slotted item. And then we're going to acknowledge that and send that to the next node, and then proceed with a publish response. So that we effectively can see that we received the state from one node into another node, and then we've made that transaction. We've actually acknowledged that. And then just on the, let's see here, right-hand side is just how we formulate that with a mathematical equation inside our TLO plus tools. So in order to provide full specification, it's not just sufficient to specify how these individual nodes behave when they receive a state, right? So it's also about how the environment behaves around that. So for the network, we consider delays, message loss, duplication, and reordering of the messages between two nodes. But for the network, we consider we also have different model failures or node failures. So we're talking about out-of-memory errors, hardware errors, Pennywise again, that guy. So we have all those model nodes so we have a model for all these particular node failures. And one way, the key achievements of the consensus algorithm is that it works correctly under the failure condition that you specified. So we consider the node crashes where it's persisted as a state loss. So finally, we also add another model for clients, which is submitting values to consensus algorithm. So this is a system that has just started up and now receiving data, and this is the different environment settings that we can set for it. Now, a lot of this, you're probably thinking, how am I going to use a set of these tools like TLO Plus or formal modeling, or even from specifications? How can I apply this on my day-to-day basis? And I kind of asked that myself because I'm not an active developer on Elasticsearch itself. So I happened to find a great example. This is a blog, and you guys can obviously see it because it's dark blue on black, right? But it's this idea of how to resolve the die-hard drug problem. Has anyone seen Die Hard with a Vengeance? Yeah? Woo! So basically, there's a concept of John McClane, which was he's a New York police officer working with Zeus, who was played by Samuel L. Jackson. They needed to stop a bomb from going off in a New York park, and they needed to have a way to solve a problem where they can exactly measure 4 gallons of water and put it on a scale to disable the bomb. Right? Very simple, everyday problems that you and I have to deal with. So they have a concept of, that was a joke. You have a 5-gallon jug and you have a 3-gallon jug. And how are you going to take that problem, how are you going to take some of that water and with those two elements and get a 4-gallon jug of water? And of course, using TLO Plus, and the blog article is really good about explaining about how you set up the mathematical equation for this using these tools and the variables and the environment variables they put behind it. And here's the possible solutions for that. So Nicholas Camus had did a nice little blog article. So this kind of helps you introduce you into TLO Plus if you're thinking seriously of using these mathematical tools to solve some of these very hard distributed or very hard problems. And on the so to go on the resiliency rule, number 5 is use math or really TLO Plus for very complex or difficult problems. So this is just an idea, and listening to everyone else talk about very complex problems and issues within their systems and the complexity of systems, I almost wonder, is it something worth going through an exercise on TLO Plus, for example, to mathematically write the problem down and see exactly what you come back with? The Leslie Lamport has, and I'll show you in just a second, a great tutorial and a web page that walks you through how using that. And after 1 to 2 days of working with TLO Plus, you can have meaningful conversations about what this data, how your system resiliency is wise, looking for bugs, and helping you with coding your application. So 2 days is giving you some meaningful conversations about resiliency in your distributed system or across multiple systems. And of course, one of the things that I also wanted to mention is that everything that we kind of talked about within this presentation was all committed to open source. So Elasticsearch is an open source product, so it's something that as you go through, and I'll put a couple links, if you want to have more information about how we came up with Zen 2, which was released in 7.0, which is fairly recently for some of the folks that don't know, on how we come together with creating a forum with Elasticsearch nodes. So where can you learn more about this? So again, Leslie Lamport was the creator for TLO Plus. He's got a great sense of these videos and how you put them together. The other great thing is he's got very dry humor. So if you like that stuff, he's all about that. But there's a great introductory course on how to do this. Of course, Amazon has formal models on how they use TILA Plus for their distributed architecture within inside the EC2 instances. And of course, specific formal models for core Elasticsearch algorithms. And this talk was also based off of Yannick Welsh. And Yannick works in Elasticsearch as a developer. And he talks more specifically on how he uses TILA Plus and goes through more of the details. And also, there's also another talk from Elasticsearch Consensus from David Werner, Yannick Welsh, Boaz Lix, and Jason Keeler. So, thank you.